Hello, everybody. Mr. Hennon here for a little Henstitute help. I'm going to basically go through the parts of this relative motion Google form because I have notes over here, but sometimes the notes feel kind of disconnected from the actual questions. So I thought I would just kind of scroll through these problems, see if that helps a little bit. So, number one says three cars, A, B, and C, are moving along a straight section of a highway. The velocity of A relative to B is VAB. The velocity of A relative to C is VAC. The velocity of C relative to B is VCB. So, they basically have described this. You're going to see this in question number two as well. So, if VAC is 40 meters per second and VCB is 30 meters per second, what is the velocity of A relative to B? So, one of the things I was trying to do was show that when you combine these together, you can do this if you basically combine those subscripts. So, I need to pull something up so you can kind of take a look at this idea. So, I'm going to pull up a nice little whiteboard that I can use. So, let's just do a quick one. There we go. Okay, so in this idea, if you are trying to find the velocity of A relative to B, then you can split this up and you can say that would be the velocity of A relative to C plus the velocity of C relative to B. So this is kind of the way you would want to do that. So if I look at what I have here, in the original problem, they say that I have VAC is 40 meters per second, okay? And VCB is 30 meters per second, okay? So 40 for VAC. Hey, look, I have VAC. That would be 40. And then if I come back, it says that VCB, in other words, the velocity of car C relative to B is 30 meters per second. So, hey, look, VCB, 30 meters per second. So really, this one's a very straightforward that if you want the velocity of car A relative to B, then you find how fast A is going relative to C and then how fast C is going relative to B, and you can just kind of combine them together. So I think that makes it a little bit easier. Now, they switch things up a little bit in part two or question number two, but a lot of the beginning is the same. So if VAB is 60 and VAC is 20, now we're going to try to find VCB. Okay, so we're trying to find the velocity of car C relative to B. I know VAB is 60 and VAC is 20. VAB, hey, let's switch this out, is 60. And carrying that over, and VAC is 20. You're trying to find VCB. So kind of just keep that in mind of how you would actually do this. So once you kind of write it like that, I think it definitely helps. So VAB 60, VAC 20. Okay. Now, another way to kind of think of this, if I were to flip around the VAC, I could write it as the velocity of car C relative to A. So here's another way I can think of this problem. Okay. So this is kind of my question. I can also say, okay, if I know that VAC is a positive 20 meters per second, that's the velocity of car A relative to C, I can flip it around and VCA would actually be negative 20 meters per second. In other words, if car A is moving in the positive direction at 20 relative to car C, then car C is actually moving negative 20 relative to car A. It's kind of like when you pass somebody, they would say that you're moving faster than them by a certain number of meters per second or miles per hour, but you could also look at them and say they're moving backward at that same speed. So that's another way to kind of look at it. So I feel like that's kind of a nice beginning to give you a feel for what we have going on here. So let's see. Number three, car A. We got another one, VAB, VCBs, and kind of do that. You can fill those in. I think you could get that one. So I'm going to do three for you. Number four. Now this one's a little bit different. So I have Swimmer A is going to swim perpendicular to the current. Swimmer B is going to swim upstream at an angle, and swimmer C swims downstream at an angle. Who crosses the river in the least amount of time? So what this is really looking at is, let's kind of clear this page out. Boom, all this stuff is now gone. So this is kind of looking at the fact that when you have a river here, actually, let's just create a new one. So I'm going to close this off. Don't save. Let's just create a new one. That way I don't have to worry about the extra little piece here. Okay, here's my river. Okay. Let's say that this is downstream. Okay, that's downstream. So I've got my first, one of my people is going to actually swim straight across. But because it's downstream, they're going to actually end up kind of be moving diagonally. They're going to end up down here. So that's where that person would end up. So this pink person is going to end up down here. Okay. The next person is actually going to swim upstream. Okay. But because of the current, what ends up happening to them is they end up going straight across. So they end up right here, because what happens is this diagonal gets combined with that to give them that for their final motion. The last person swims downstream like that. And then with the stream actually pushing them, they're going to end up somewhere way down here. So I think you can understand that this person right here is definitely not going to do it in the least amount of time. They are going this great distance way. They're going faster, but it's just not working. The main idea is really, if you're crossing the river, the only thing that's important for crossing the river is your velocity straight across the river. Okay? So in this particular situation, they have kind of this diagonal, but their only little bit that's straight across the river is this part. This one, all of it is straight across the river, and their little bit across the river is this one. So in this particular problem, what you should see is the one that actually has the greatest amount, they all swim equally fast relative to the water, that the person that is actually these components of their diagonal velocity are going to be smaller than this component right here. So this person that's actually trying to swim straight across would have the greatest velocity straight across, even though they're going to go diagonally downstream. That's kind of the idea. Okay. Okay, last but not least, let's take a look. Person looking out the window. Have you ever done this? Looked out the window and you see water kind of going diagonally across the window there? We can figure out how fast you're going. So if the raindrops are falling vertically at a speed of 5 meters per second relative to the ground, when the train moves at a constant velocity, the raindrops make an angle of 25 degrees when they move past the window, as the drawing shows. How fast is the train moving? So if you notice, they actually show this kind of with the water kind of going diagonally like this. Well, I know straight down is 5 meters per second. We want to figure out the velocity of the train. But actually what we're getting is the velocity of the raindrops relative to the train, but we actually want to know how fast the train is going relative to the raindrops. So that's kind of we want the reverse of it. So that's actually where it comes from. But really, all you got to do is find the horizontal component of this little triangle. So again, coming back to this, I'll just put it right down here. If I have the rain coming down at 5 meters per second, but it actually produces kind of this diagonal pattern, that's because I have some kind of horizontal velocity. This would be the velocity of the train. And I know this is 25 degrees. Let's just figure out what this is. So that side is 5. That side is, I don't know, 25. It's going to be a nice perpendicular angle. So it's going to be a right triangle. And you got it. Hope that helps.